Hello, everyone. Welcome to this webinar called ANC Headphone Testing. My name is Santiago Rashes. I'm part of the Global Technical Support team, and my position is Global Support and Applications Engineer for both Audio Precision AP and GRASS. So first, some housekeeping things to remember. As you probably noted, all your microphones are muted, so you can't speak during the presentation. But if you check the dashboard of this GoToWebinar platform, you will find a questions section where you can write all the questions you have. We're going to make some time by the end of the presentation so we can check and answer the questions. If there are some questions that we can't answer because of lack of time, then we're going to answer them via email. But of course, you're always welcome to contact us, for example, via email at support@grassacoustics.com or tech support@ap.com. You will also find a handouts section in the GoToWebinar dashboard where you can download a PDF copy of this presentation. And finally, this webinar is being recorded, so you're going to receive a copy of the recording in a couple of days from now. So without further ado, let's look at the agenda for today. First, we're going to look at some very basic definitions about ANC. We're going to look at all the relevant standards. Particularly, we're going to put the focus on the ETSI standards and its recommendations for the measurements, and we're going to make some comments about it. First, we're going to look at how to perform an insertion loss test for ANC. We're going to look at some GRASS test fixtures and compare them. We're going to discuss about the main or the basic challenges regarding ANC testing, and we're going to look at some test setups using audio precision analyzers. By the end of the webinar, we'll have a short video demonstration on how to do an insertion loss test using the APX 500 software by AP. And last but not least, we're going to have the Q&A section. So let's look at some very basic definitions. Let's concentrate on the top of this slide on the insertion loss. So basically, in acoustics, when we talk about insertion loss, we are defining a reduction in the noise level at a receiver's position. And this is happening due to the placement of an attenuator in the sound path between a sound source and a receiver. Now, in the context of a headphone testing, particularly ANC, the sound source is going to be the environmental noise. For example, the noise in the coffee shop and the traffic noise. And the attenuator is going to be the headphone itself, while the receiver is going to be the ear canal of the person that is wearing the headphone. When it comes to noise cancellation, we can divide this into two different concepts: passive noise cancellation, PNC, that is happening due to the materials of the headphone that are physically blocking the sound from entering the ear. But not only that, also how the headphone or headset itself is sealing the ear canal or the pinna from the person that is wearing the device. On the other hand, we have active noise cancellation, also called ANC, that is happening due to a device that is generating sound waves at the receiver position, let's say the ear canal, and these sound waves are combining destructively with the sound waves that are penetrating the headphone from the outside. So you basically have the sound waves that penetrate the headphone, and then you have the sound waves that are generated by the ANC algorithm inside the ear canal, for example, what we call the anti-background noise, and the result, and this combined destructively, having this lower sound pressure level inside the ear canal of the person wearing the headphone. When we are measuring a combination of the PNC with the ANC, we'll be measuring the total noise cancellation. Now let's look at some relevant standards. I think nowadays the most important standard with recommendations of testing ANC is the ETSI TS 103-640, Speech and Multimedia Transmission Quality, Test Methods and Performance Requirement for Active Noise Cancellation Headsets and Other Earphones. This standard itself, we're going to look at it in the next slide. It's referring to other standards that we have here, particularly when it comes to the acoustic test fixtures that we have to use for the ANC performance test. And one of these standards that it refers to is the ITU-T P57, that it describes different types of ear simulators and artificial ears and divides them into different categories. On the other hand, we have the ITU-T P58 that describes different types of head and torso simulators, and the ETSI standard is recommending to refer to the P58 if we have to decide on a specific type of head and torso simulator. We also have other important standards, such as the IEC 6318-7, that also specifies head and torso simulators. And last but not least, these two standards that are not regarding ANC, but instead related to hearing protection measurements using the insertion loss method. These standards have been used for a long time as inspiration for test setups for ANC testing. So if we have a proper look at the ETSI standard, we will find out that it's divided into different sections, and it's giving us recommendations for testing many different things. It's not just insertion loss testing for passive and active noise cancellation, but we'll also refer to the ANC in terms of loudness that takes into consideration a psychoacoustical parameter that considers the sensitivity of the human ear at different frequencies. And not only that, but also measure the ANC circuit noise, the self noise of the device. We're going to see how the ANC algorithms will affect audio playback, for example, and also many recommendations on how to test the voice call performance and the pass-through mode as well. Of course, we don't have time to look into everything. We're going to put the focus on the artificial ear part, and also some basic concepts related to insertion loss measurements. The ETSI standard is requiring the use of a special room, particularly in terms of background noise. So the background noise in the room doesn't affect the measurement itself. The basic parameter that we are using for testing ANC is insertion loss. So we are going to look at this method. Of course, we are measuring noise cancellation in terms of ANC and PNC. And not only that, but also, as I mentioned before, we're going to be measuring the ANC circuit noise. The standard recommends the use of a head and torso simulator, like the GRASS KeyMar that we see up here in the slide. And some tests, particularly the ones related to the pass-through and the voice call quality, will require the use of a mouth simulator like the GRASS 44AA or 44AB, or a head and torso simulator equipped with a mouth simulator like the GRASS KeyMar 45BC. This is the typical setup in a room with 8 loudspeakers that will play back a reference noise signal. The head and torso simulator is placed in the middle with a device under test, or headphones, and then we're going to have a system that will feed the loudspeakers with a noise signal, and we're going to connect the head and torso simulator to the data acquisition system. that's going to be receiving the signals from the ear simulators inside the head and torso simulator. Let's look at the ANC headphone testing in terms of the insertion loss test. As I mentioned before, we're going to have a test signal that is going to be used to create the noise field. This could be a very basic reference signal such as pink noise, or it could be a realistic signal such as noise from the metro, noise from the coffee shop, noises from the street, and so on. We're going to perform the measurement in terms of a frequency response test. It could be an FFT, but it could also be an octave analysis such as third octave or 1/6 octave analysis, depending on the resolution we would like to have. The important thing is that we always specify exactly what we are using for a test. So the test is divided into different steps. The first step would be to place the head and torso simulator in the center of our testing room. We're going to be measuring the ambient noise of our room with the test signal turned off. The next step would be turning on the test signal without placing the device under test, our headphones, on the head and torso simulator to measure the baseline noise with the open ear. The third step would be to mount the headphones on the test fixture. We're going to turn on the reference signal and measure with the ANC turned off. The next step would be the same, but turning on the ANC. And then we're going to calculate the signal to noise ratio by doing the following math. Step 1 minus step 2 will give us the signal to noise ratio. Passive noise cancellation, or the light blue curve we see up here, is going to be the step 3 minus step 2. And the total ANC plus PNC calculation will be step 4 minus step 2. That will give us the violet curve we see up here. Now we have some comments related to the ETSI standard. At some point, the standard is requiring us to choose the type of artificial ear that we would like to use for the test. And it's referring to the ITU TP57. We can either choose type 4.3, a type 4.4 artificial ear, or a type 3.3, this one over here on the left. If you're familiar on how to specify the transfer impedance of artificial ears, you will be familiar with these types of transfer impedance curves. In this case, the information I'm displaying is the same, but it's displayed in a different way. The only difference between this graph above and the graph below, the only difference between these two charts is that the charts below is the transfer impedance is multiplied by the frequency, but they are both displaying the same information. So this is showing us the transfer impedance of the artificial ear versus the frequency. And here we can see the tolerances in the dashed lines for the ITU P57 standard. Sometimes we can be worrying too much about which type of ear, artificial ear, I'm going to use. It's going to be a 4.4, a 3.3, a 4.3. But I think in some cases, it's more important to be able to properly define the positioning of our device under test in the ear canal, particularly for in-ear devices, because as we can see here on the chart on the right, just a 2 millimeter variation from the reference point being the black dash curve over here, just a 2 millimeter variation from the positioning will give us a completely different transfer impedance that in some cases will be outside the ITU specified tolerances. So with this, we could say that maybe it's not that important to worry about the particular type of ear that we would like to use if we can't really control the exact position of the device under test inside our artificial ear. Another thing that the ETSI standard is mentioning is that the noise floor of our artificial ear simulator should be less than 7 dB SPL A weighted. Now, when it comes to specifying noise floor for measurement microphones, preamplifiers, and ear simulators, we can have the noise floor of the preamplifier alone. We can have the noise floor of the microphone capsule alone, but microphone capsules are never used without a preamplifier. So we need to consider the combination of the noise floor of both the microphone capsule and the preamplifier. The total noise for this combination is always a little bit of a noise from the microphone capsule itself, and then a little contribution as well in low frequencies from the preamplifier noise, and that will give us the total noise. Then in some cases, when the microphone capsule and preamplifier are placed inside an ear simulator like this 711 coupler we see up here, the noise figures could change as well. So we need to look at the specifications that the manufacturer is giving to us. Here's an example. For example, the noise floor of a microphone capsule alone is 20 dBA, but in a realistic situations, the microphone capsule will be always used together with a preamplifier. And when we consider the noise floor of the preamplifier and microphone capsule combination, the noise is increasing from 20 dBA to 25 dBA. Now, let's look at this ANC measurement following the insertion loss steps that we saw before. In this case, we're using a 1/2-inch pressure microphone with a preamplifier that is mounted inside a 711 coupler, just like we see up here on the top right. If we look at the ANC results down here on the right, we might think that the ANC and the PNC results are giving us the same result above 8 kilohertz, but actually this is not true. This is actually a limitation of the noise floor of a system we are using. As we can see here, this is the noise floor of a typical combination of 1/2-inch microphone plus preamplifier inside a 711 coupler. That means that we can't really trust on the results that we are measuring above 8 kilohertz. If we consider the type 4.3 coupler specified in the ITU P57, the problems can go even further, because this coupler is based on the use of quarter-inch microphones. And quarter-inch microphones will have a higher noise floor. If we're talking about 25 dBA, typical noise in 1/2-inch microphones, quarter-inch microphones, or the typical noise floor for quarter-inch microphones is around 44 dBA. We do have special high sensitivity quarter-inch microphones, but even in these cases, the noise floor is not going to be better than a 1/2-inch microphone and preamplifier. So this is something we need to consider. So let's look at why the standard is mentioning this 7 dB SPL-A figure. Well, basically, it's based in a system like this, like the GRASS 40HT. That has, this is a combination of a microphone capsule with a preamplifier, and it's giving us 6.5 dBA. This is a very special microphone, very high sensitivity device that can give us a very low noise floor of 6.5 dBA. So this figure we see over here is based on a solution like this, like the GRASS 40HT. The problem is that when we place a system like the GRASS 40HT inside an ear simulator, like we have in a GRASS 43BB low noise ear simulator, the noise floor will be increasing from this 6.5 dBA figure I mentioned before to 10.5 dBA. And this is partly due to the thermal movement of air particles in the front volume of the coupler. So unfortunately, given the state of the technology nowadays, if we are using an ear simulator, it's not possible to get those the noise floor that is recommended by the standard of 7 dBA. The best we can do is 10.5 dBA with this very specialized type of ear simulator with very high sensitivity. If we repeat the measurement, the insertion loss measurement I showed you before with the same device, but now using a low noise system like the 43BB, we can see that now above 8 kilohertz, we can see a difference in the measurement between the ANC and the PNC. I don't know why we have or why we are measuring this difference. That's probably related to how the algorithm works. But the good thing is that now we can actually measure something, and we are not limited by the performance and the noise floor of our ear simulator, microphone, and preamplifier combination. So this is something to consider as well. Here's a measurement of the ANC circuit noise. So when we turn on the circuit noise of an ANC device, we probably hear a hiss noise, and we are trying to measure that. If we try to measure that with a standard 711 coupler, half-inch microphone, and preamplifier, we're going to end up measuring the noise floor of the system itself instead of the noise floor of the headphone that we are trying to measure. For those type of measurements, it's always recommended to use a low noise system such as the 43BB. In this case, thanks to the very high sensitivity and very low noise floor of the 43BB low noise ear simulator system, we will be able to measure the hiss noise created by the ANC circuits. So as a summary from this section, the 6.5 dBA performance is only possible for a microphone plus preamp combination, but not for the complete ear simulator, microphone, and preamp combination. In that case, the noise floor that we can achieve with the current state of technology is 10.5 dBA. In order to use one of these systems like the 43BB low noise ear simulator system, will require artificial ear type 3.3 or 4.4. Unfortunately, the 4.3 system, as it's based on a half-inch and on a quarter-inch microphone, cannot be used for such measurements. Here, I know we have a lot of information, so I will try to explain. First of all, let's get rid of all the data below 100 Hertz because here we have a limitation on this particular test chamber. So what we see here, it's basically a head and torso simulator placed inside an anechoic chamber. First, with the open ear, without the headphones, we're going to be measuring the background noise of the chamber, and that's the blue curve we see here. Then we mount the headphones with the ANC turned off, and we measure again the noise floor, and this is the red curve we see over here. Then we're going to turn on the ANC. This particular headphone has two profiles, low ANC and high ANC. And just by turning them on, we're going to see that we'll have some noise This is the hiss noise that I was mentioning before, and this is only happening due to the active circuits of the ANC. If we compare this with a black curve that is basically showing us the human ear sensitivity, we can see that part of these noisy signals we will be able to hear with our ears. So this could be annoying, and this is some signals that we are going to try to characterize so we can improve and reduce as much as possible and push them even lower than the human ear sensitivity. If we look at the noise floor of a standard 711 coupler with a half-inch microphone and preamp, we can see that it's going to be impossible with such system to measure those signals because they are below the noise floor of that system. The problem is even worse when we use a quarter-inch bass system because the noise floor tends to be even higher. But then let's look at the noise floor of the 43 dB low noise ear simulator system. So you can see that now with such a system, we'll be able to measure the ANC, the self noise circuit noise. And therefore, we will be able to measure what we can actually hear. Another consideration when it comes to the ETSI standard is that the standard recommends the use of a head and torso simulator that has at least 35 dB of attenuation. The attenuation of the test fixture will be reduced by leakage that can be happening through the joints in the scalp or the joints in the pinna or the mouth simulator opening or the neck joint or vibration transmission through the torso as well. If we consider the worst case scenario where we are following the recommendation of just 35 dBA, we need to consider that if we have a high performing device like we see over here, then we won't be able to measure anything that is above this dash curve. So it's always better to get a head and torso simulator of a test fixture that has, of course, higher attenuation than just 35 dB. If we just follow the 35 dB rule, we're going to have limitations with measuring many devices. So here we have a comparison with another test fixture, in this case, the 45CV. The 45CV is not made according to ITU P58 like the KEMAR. It's made according to the ANSI 12.42, which is made for tests of hearing protectors under explosive conditions, impulsive noise, for example. And we can see that the self-insertion loss of the fixture is much higher than the minimum recommended of 35 dB. So it's even higher than 60 dB. So this is a great test fixture if we would like to test high-performing devices. What we need to consider here is that the fixture is not made according to ITU P58, but the fixtures made according to ITU P58 tend to have way lower self-insertion loss. So this is something to consider as well. So as a summary, we can say that the positioning of the device in the ear canal, for example, when we are talking about in-ear ANC devices, the positioning is critical, but it's actually not specified by the ETSI standard. The specifications are related to the ITU TP57, and they are giving only one plane, the reference plane. But if we move the device a couple of millimeters away from the reference plane, the transfer impedance curve is going to change significantly, as I showed you before. Low noise ear simulators like the 43 dB are recommended whenever we would like to measure the self noise of ANC, the ANC circuit noise, and also high self-insertion loss test fixtures are recommended for high-performing ANC devices. Here we have a comparison between different GRASS test fixtures. The 45BB, 45BC KEMAR is the one made according to ITU P58. This one can be equipped with a low noise system if you want to measure ANC circuit noise. The only limitation with such device is that the self-insertion loss of the fixture itself is around 40 dB. If we have a very high performing device, we could be using something like the 45CB or the 45CA that have way higher self-insertion loss than the KEMAR, as we can see here, 65 dB and more than 60 dB for the 45CA. The limitation here is that they are not an ITU P58 standardized test fixture. Some challenges to take into consideration. First of all, as I mentioned before, the high self-insertion loss of a test fixture is something that we need to consider. In some cases, some customers are forgetting about this, and they might be actually measuring the self-insertion loss of the head and torso simulator itself instead of measuring the actual performance of the ANC device. So always check on the specifications of your test fixture, like your head and torso simulator, and double check that your test results are not being limited by the self-insertion loss of the test fixture. We can't forget about the dynamic range of the combination of our microphone, preamplifier, and ear simulators. First of all, we have to consider the upper dynamic range limit, that is the maximum sound pressure level that they can measure. We need to consider that, for example, in cases that we would like to test with very high sound pressure levels. Let's say if we want to test with signals close to 120 dB, for example, 130, most ear simulators won't be able to deal with such a high sound pressure level, and we'll probably need to look for other solutions. And the same for the self noise of the device. As I showed you before, it's important to consider the noise floor of our microphone, preamp, and coupler combination whenever we would like to measure very low sound pressure levels, like the measurement of the ANC circuit noise. The ceiling of the device under test of our headphone or headset around the ear canal and the pinna, it's very important, because if we have some leakage, the ANC measurement test result is going to be unreliable. So we need to check that we are achieving proper sealing. So this is usually could be related to bad mounting of the device on the test fixture, or it could be a problem with the design of the device under test itself. So this is something we should look into it. Realistic soundscapes versus simple reference signals. As I mentioned before, you can use a realistic signal such as the noise from a coffee shop, traffic noise, or we can use a very simple reference signal such as pink noise. It could be that some devices will perform in a very different way if we are using a realistic soundscape versus a simple signal like pink noise. So this is something that we should look into it. The test environment, and particularly the background noise, it's important to measure. If we have high background noise, that will affect the reliability of our measurements. For the wireless devices, such as Bluetooth devices, will require will require to use an analyzer that has the possibility of communicating directly with the device. with a Bluetooth interface. So this is something that should be considered. ANC performance, as mentioned in the ETSI standard, can be measured in terms of insertion loss or in terms of loudness. It's not always the case that the device that better performs in the insertion loss test will be the device that better performs in the loudness test. The loudness considers the sensitivity of the human ear at different frequencies. It's a sound quality parameter. So this is something to consider as well. The audio playback can be deteriorated when the ANC is turned on. Then again, the ETSI standard has recommendations about how to measure this. And last but not least, particularly the newest ANC devices will come with adjustable or adaptive ANC that might change over time depending on the changes on the environmental noise. And once again, the ETSI standard gives us some recommendations on how to perform measurements for this type of ANC. Here we have the typical test setup recommendation by the ETSI standard. The room with low background noise, our ITU P58 head and torso simulator surrounded by the 8 loudspeakers will have a system that will be in charge of creating the background noise simulation that will gonna play back the signals through the 8 loudspeakers, and we'll have the other system that is gonna be connected to the ear simulators, ITU P57 standardized ear simulators in our head and torso. For some cases, such a setup can be overkill or can be too complex, particularly if we would like to perform a quick R&D test or we would like to test the ANC in a production line environment. And that's why sometimes the complexity is reduced with setups like this one we see on the next slide. This could be this test could be performed in a small test chamber with a single loudspeaker. Instead of using a realistic soundscape, we could be using a simple reference signal such as pink noise, and we can use a small test fixture such as the 45CA, for example. So this is a recommendation for whenever we would like to reduce the complexity of the setup, or maybe we would like to have quick and dirty results related to ANC performance. But then again, this is not something that is recommended by the ETSI standard. The ETSI standard is only giving us this very complex setup that we see here. When it comes to audio precision analyzers, we have different recommendations of what you could use. If you would like to recreate the setup mentioned in the ETSI standard, you could be using something like this with an APX585 analyzer that's going to be having 8 analog inputs and 8 analog outputs. The 8 analog outputs can be used to feed the loudspeakers together with an audio amplifier or amplify loudspeakers. And then in this case, we'll require a small power module to get the signals from the ear simulators, as the APX585 doesn't have microphone inputs. On the other side, for a more simplistic setup, we can use the APX517. Here we have a built-in audio amplifier to feed a single loudspeaker, for example. We also have built-in stereo headphones if we would like to test wire headphones. We have 2 microphone supplies where we can connect the ear simulators coming from the head and torso simulator. And but the thing to consider here is that we only have a mono audio amplifier. and only 2 microphone inputs. In both cases, we have the possibility of adding digital channels. Just like we see on the top, we could be adding something like an HDMI that can be used as an output for a multi-channel signal to create a realistic soundscape with multiple channels. For example, we could be using this HDMI module both in the APX 585 or in this single slot that we see here in the 517. Otherwise, if we're working with Bluetooth headphones or headsets, we could be using the Bluetooth Duo module, and this could be used also here in the APX 517 or the APX 585. With such configuration, we'll be able to directly connect to a Bluetooth headphone and headset and send signals to the headphones, or receive the signals from the microphones in the headset as well. These analyzers are used together with the APX 500 software. All the AP hardware analyzers will include a perpetual license for the current version of the APX 500 software, plus the next version as well. We also have a subscription license model for a year, for 3 years, or for 5 years, so you can always get the latest version of the measurement softwares. We are basically releasing one major update of the software every year for the last 15 years plus. Basically here we can have a one-click automated measurement, and we have a huge collection of measurements for both electronic audio but also electroacoustical tests. It's not required to know anything about coding or programming, but if you would like to program your automation, or because you want to merge the APX software together with another automation software, you could use our APX API, and you can program in any VB.NET compatible language such as C#, MATLAB, you can use LabVIEW, you can use Python as well. So basically we are offering a common software platform that can be used both in R&D situations but also in the production line. So without further ado, I would like to show you a very short demonstration on how to use the APX 500 software to perform an insertion loss measurement. This test is related to this tech note 141 that you can download by clicking on this link. You remember to go to the handouts section of the platform, and you can download the PDF copy, and you can access to all these links. I'm basing this measurement in the example setup 2 in the simple test setup, and the idea with this video is that you have a basic idea on how the software works and how you could perform the measurement. Please check your PC's audio settings, because if you don't hear anything when the video starts, it could be that you're sending the audio to another device. So if you don't hear anything, go to the PC's audio setting, not the GoToWebinar audio settings, just the PC, like the Windows audio settings, and select the right device that you would like to use. So without further ado, let me share the video with you. I'm going to be using signal path number 2 for the ANC measurement. I will expand the signal path to see what's included on this sequence. And as you can see, besides the signal path setup, I have 2 different measurements that are the basics for this sequence. First of all, I'm going to be performing a signal to noise ratio measurement, and then the ANC measurement itself. So now I'm going to run the sequence. The first thing is that I get a prompt to insert the ID of the device under test. That could be the serial number of the headset. I'm going to press OK.
Then I get, once again, a wiring diagram to double check the connections. I'm using a 45CA that has 2 ear simulators that are connected directly into the microphone inputs 1 and 2 of the APX 517 analyzer. And I'm using a single full range passive loudspeaker that is connected into one of the outputs of the power amplifier that is built in the APX 517 analyzer. For this test, I'm going to be using a pink noise reference signal. That doesn't mean that I can't use another reference signal, but for the sake of this test, I would like to keep it as simple as possible, and that's why I'm using a single mono output with a pink noise reference signal. So as I told you before, this sequence includes a measurement that is called a signal-to-noise ratio measurement. For this measurement, the system will first of all measure 10 seconds of the background noise within the test chamber, and then another 10 second with the reference signal turned on. As you can see, the device under test is still not mounted on the test fixture. So that was enough to measure the signal to noise ratio. Now it's time to measure the ANC performance. And as you remember from the presentation, the first situation would be the open ear measurement, where the DUT is still not mounted on the test fixture. And I'm gonna play the reference signal in an open ear situation. So for the next step, it's going to be situation number 2, where I have to carefully mount the headset on the test fixture with the ANC function turned off. And for the third situation and final step, I'm going to keep the headset mounted on the test fixture, but I'm going to turn on the ANC function. So once the measurement is finished, we get this nice report. So the sequence was configured to create a measurement report where we can see all the results. Of course, this report can be configured in any way you prefer, adding more or less results to the report itself. Let's go back to the APX software and let's analyze all the different steps corresponding to the ANC measurement sequence. So as you can remember, the first measurement we performed is the signal-to-noise ratio measurement. In order to do that, there was no DUT mounted on the test fixture. Under these conditions, we measured the noise floor in the test chamber. This is measured from the ear simulators of the test fixture. And then we turned on the signal generator with the reference signal, which was a pink noise signal. With these two measurements, we can calculate the signal-to-noise ratio, and we can analyze if the results are good enough for the measurements we are about to perform. So the next measurements are the ANC performance of the DUT. So this result we see over here shows the 1/6 octave spectrum for the 3 conditions for the left and right ears. Let's remember the 3 conditions. The first one is the open ear situation with no DUT mounted on the fixture. Then we have the second situation that corresponds to the DUT mounted with the ANC turned off, which corresponds to the passive attenuation of the DUT. And for the third situation, we have the DUT mounted on the test fixture with ANC on. This corresponds to passive plus active attenuation. To make sense of these results, we can use a compare derived result within APX to normalize all the results to the open ear result. So here I'm showing you the results for the left earphone. The blue curve is the open ear result compared to itself, which will constitute an open ear reference. Then the blue curve is corresponding to the DUT mounted on the test fixture with the ANC turned off. This is a passive attenuation. As we can see in this lower part of frequency range, there's a resonance going on, and this is because of the cavity of the headset itself. And then on the green curve over here, we have the performance of the DUT with the ANC turned on. So this is showing us the passive plus active attenuation. So this DUT has some attenuation going on compared to the passive result, up to around 1.5, 1.7 kilohertz. This same result is shown for the left and the right earphone, and they are also expressed as insertion loss results if we want to. So this concludes the demonstration for the ANC test performance, and we can go back to the webinar.
So once again, this is just so you get a basic idea on how the software is used if you're not familiar with it. If you would like to see more details about this particular measurement, you can then again refer to the Tech Note 141, and here you can find the link to download this Tech Note. The Tech Note comes together with the APX project files. If you are not having an APX analyzer, you can always still download the software from our website and use it in demo mode, so you can investigate the project and look at the automation and how everything is performed as well. So that was the last slide from this webinar. Thank you very much for participating. Here I'm going to leave some links to very useful material. We're going to have this headphone test application note, which is a very extensive description on how to perform many different types of measurements in headphones, and not only ANC measurements. We also have a video that shows how to perform headphone measurements using the APX 500 software. We do have a lot of audio precisions training videos in our YouTube channel, and here I'm also leaving you a link where you can see all the different grass test fixtures for headphone testing. Now I'm going to look at the questions and see if there are any questions here. Someone is asking if we can share the slides after the training. Yes, actually you can download the slides right now if you go to the handouts section, and you will have a PDF copy. Yeah, and we are also going to share the video recording in a couple of days from now. Someone is asking, is the 45cc complies with the ITU P58, and if not, could you please explain why not? No, the 45cc does not comply with the P58. If you look at the P58 standard, actually you can download it from the ITU website. You will see that the standard clearly indicates what's the shape of the head and torso simulator. So it has to have a realistic, human-like shape, like the grass skimmer, and that's basically the main reason why a test fixture like a 45cc does not comply with a P58. Then again, this doesn't mean that you can't use the test fixture like a 45cc or any other test fixture that doesn't comply with a P58 for headphone measurements. As I show you, the ETSI standard is not perfect. And in some cases, it might be even better to use another test fixture, like I show you in the cases where a high self-insertion loss test fixture is needed. Is there any plan to support Bluetooth LE? Well, I can't give you any information about that. I can tell you that we're always looking at the latest developments, particularly when it comes to Bluetooth. So I recommend you that you check with your sales representative in your region to see if we can give you any more information about that. Could we circumvent the head and torso simulator microphone noise floor 7 dBA spec given by the ETSI in an ANC measurement by increasing the generated noise level? For example, we can measure at 85 dBA. Yeah, I mean, you could do that, but that's the main reason why you need sometimes to use an ear simulator with a very low noise floor. It's in cases like the one I showed you during the presentation, where you want to measure the ANC circuit noise. So the ANC circuit noise is happening. Let's say I'm putting my headphone in a very quiet environment, and then I turn on the ANC, and just by turning on the ANC, I might hear some hiss noise. So these are very low sound pressure level signals. So there's no way around that. You will need to use an ear simulator with a very low noise floor in order to be able to measure these signals. I'm checking on more questions. Is there any recommendation in ETSI standard regarding the noise signal type? Well, yes, it actually proposes different types of signals. One of them is a very simple pink noise, and another signal is, I don't remember exactly, but there are some realistic signals such as traffic noise and things like that. Then again, you can go to the ETSI website and have a look at the standard. I don't think you have to pay for in order to see this standard. Just like with the ITU TP58 and the P57. But yeah, it actually gives you recommendations for different types of noise signals. Would Octave Analyzer do the hiss noise measurement setup as well? If so, what resolution would be sufficient? Yeah, actually, you can do it in third on 1/6 octave as well. And that's not what's limiting if you can measure the hiss noise or not. Actually, the bottleneck for the measurement, as I mentioned before, is the noise floor of the combination microphone capsule, preamplifier, and ear simulator. So if the noise floor of your system is 20 dBA and you are trying to measure a signal of 50, then you won't be able to measure that signal because it will be masked by the noise floor of your system. So it doesn't matter if you're using an octave analyzer or an FFT. Will you have some introduction of ANC tuning? Well, it's not something that we are typically doing, but we're always considering ideas for new webinars. So we are going to take note of that, and thank you for that. For the manufacturing test, except the noise from ANC circuit, do we need to consider the noise isolation of the AC power supply, especially in some case we have to connect the DUT with cables for communication purpose. Uh, Actually, it would be better if you send me an email. Here you have support at grassacoustics.com or tech support at ap.com. You can better explain what's going on. Maybe we can help you out. How do you check if the headphones have leakage? Well, a typical way of doing it is by checking the low frequency cutoff of your measurement. Typically, if you will have some leakage, you will see a big roll off in the low frequencies. However, I think we do have a technical note, or maybe it's included in the headphone test application note, a simple test with a reference signal where you can check if you have leakage. So please send me an email, and I will see if I can find this document for you. I have a question. How relevant is the room? Is it absolutely necessary to have an anechoic chamber for ANC testing if your DNR is good enough? Actually, no, it's not necessary to have an anechoic chamber. And this is also explained in the ETSI standard. The standard itself is not requiring you to use an anechoic chamber. It actually, the only thing it's specified, as far as I remember, is the noise floor of the chamber that you need to have. Remember that the ETSI recommends using 8 different loudspeakers surrounding the head and torso simulator. That means that the sound field can be fine-tuned by changing the amount of signal that is played back through the different loudspeakers. So I recommend you to check on the ETSI standard, and the short answer is no. You don't need to have an anechoic chamber if your room is well isolated. Thank you for the nice training. What about the left-right results average? I don't know exactly what you mean by that, but in headphone testing, we tend to perform multiple measurements of one device. We might place the headphones in place, we might remove them and place them again, and take a lot of different curves, and then we'll average the left result and the right results. We can take 5-10 measurements depending on if we're working on an R&D situation, if we're in production line testing, and so on. How much time do we have to test the device? How many speakers can the AP517 support? Well, you have a stereo amplifier for the headphones, and then you have a mono power amplifier for a loudspeaker. So in that case, if you would like to use a mono signal, then it's going to be only for one loudspeaker, particularly because the power amplifier is not it's not a 100-watt power amplifier. Nevertheless, as I mentioned before, you could work with digital signals, for example. So if your 517 is equipped with an HDMI interface, then you could use the HDMI output and send, for example, 8 different channels of digital signals to a digital amplifier, or amplify loudspeakers that can work with the signal coming from the HDMI. So that could be one way to have a multi-channel output with the APX517 analyzer. Thank you very much, everyone. Oh, I have another question that just arrived. What kind of reference sound can we use instead of simple pink noise? Can we find other standards? Well, then again, I would recommend you to go to the ETSI website and check on this ETSI standard for ANC testing. They are recommending not only the use of pink noise, but also some realistic soundscapes, and they are described exactly in the standard. So I think that would be the best place to check about that. For doing the 711 coupler calibration noise at 300 and 500 hertz is higher, I wonder if it's the reason of careless drop. I actually don't understand your question, so if you can send me an email, we can clarify. The 711 couplers are typically calibrated in sensitivity referred to 250 hertz. The historical reason of doing that is because piston phones that are used in calibration labs are using typically 250 hertz as reference signal, but it's also technically a good idea because the transfer impedance and frequency response we're measuring for 711 couplers at 250 hertz, it's still fairly flat compared to other frequencies like 1000 hertz and above, for example. So we ran out of time. We had a lot of questions. Thank you once again for attending. If you have more questions, you're welcome to send them to these two emails you see on the bottom right of the screen. My name is Santiago Rashes, and thank you for attending, and see you in the next webinar.